I'm here today because I won the finance section of the 2016 problem-solving competition, and I thought I'd start off by telling you how did I discover APL. And as was just mentioned, 18 months ago I was sitting in front of Morten, and he was explaining how this language was so elegant and precise and could do things in one line that C programs did in 15 to 100 lines, and I was sitting there not quite understanding, how this was actually significant. But that's where it all started, really. I met Ilse Nell that day, and she offered me a chance to come work for her in Joburg. Essentially, she dared me to drop out of university, which I did. And 2 weeks before registration, I packed my bags and moved up to Joburg. And I spent the next 2 months working through this book here, which became my Bible. And it was great. The competition sort of matched my progress, the competition last year. I would, as I'd work through this book, learn new functions. I'd sort of apply them to the problems given by Dyalog, and it was sort of a way to match my progress. After about 2 months of working through that book, I had enough of grips with the language to be given a proper project, and I thought I'd just mention this quickly. And it was an interest rate forecasting system. I was given a prototype that was written in 40 hours for the company I was working for, and I was asked to sort of pick it apart and see how it worked, essentially. And in doing so, I came across this piece of code. I think when I found that, I realized I'd probably have to rewrite the whole thing. But yeah, onto the competition. So this year's competition was set up differently. There was 3 categories. You've already heard from the general programming and the bioinformatics, and I was part of the finance section. And as you know, it was split into 2 stages. There was stage 1, which was short one-line problems. And then to follow that, there was stage 2, which were slightly more difficult problems. And for this, I thought I'd just throw in 2 of these problems. The mean, essentially it's not a difficult calculation. And I think I wrote something like that. But because this is the problem-solving competition, it's about doing it in the most elegant way possible. Ended up with something like that. And then the median, I thought I'd throw this in here. It's not exactly the nicest looking function, but it just describes the way, at least the way I think about APL, because it allows you to think in shapes. And what's going on here is, with this little rotate, you're able to pull the 2 important numbers, because the median is just 2 important numbers. There's either 2 numbers in the middle or there's 1. So you can pull them to the front of the vector, and then depending on the parity, you can just pull it off. And that's kind of why I appreciate this language, the way you can think about things moving as the shape of the data. And then just for fun, I've made this little one playing around with recursive formulas. So phase 2, there were 3 problems. There was calculating a forward rate, there was a triangular distribution, and some Monte Carlo modeling. So the forward rate, essentially we had to implement this function here. And in my mind, that just screams 2 minus scan. So that's the actual function. And as you can see, it does a 2 minus scan a couple of times, and then concatenates the first result back onto the front, because that doesn't change. And here you got your right argument being a vector of the rates, and your left argument vector of maturities. And I quite like that. The second problem was slightly more interesting. It was a probability density function, particularly the triangular distribution. So essentially a triangular distribution is defined by 3 numbers: the lowest, the mode, and the maximum. And from that you get this distribution. I think when I started this problem, I had a piece of scrap paper, and I was thinking about the different possible cases that I would encounter, and would the area be on the one side, or would the area be on the other side? Would the area reach the middle? Would it reach one of the endpoints? And kind of in the back of my mind, I thought I might have to go through about 6 cases. Here's the actual function in the end. I realized I didn't have to go through the 6 cases. Ended up with this piece of code over here, which I quite like. So essentially, that splits up the interval that you're looking over. Sorry, I don't think I explained the problem. The problem is you get an argument of an interval, so 2 points, and find the probability that your probability density function falls within this interval. And so, using these floors and ceilings, you only have to calculate 2 intervals, because the important parts essentially are these lines, because that's going to depend on the size of the area. And so I thought I'd throw in an example. If you had something like this, where you've got an interval that actually falls outside of the density function and one that falls inside, and you want to calculate this piece of area here, you still got to calculate you're going to calculate all the area that falls over here and all the area that falls over here, using these floors and ceilings. As you move through, you see that the one on the right is the area between M and M, and essentially comes out as 0, and then on the left you end up with exactly what you wanted between A and the blue line. So the final problem was some Monte Carlo modeling, and I thought I'd quickly just mention this because there was a problem brought up, I think, by Stefano yesterday. This is part of what I implemented in the ifs project that I did for RiskFlow. And essentially it's the same problem that I was speaking about yesterday, how to fit some JavaScript interactive graphing into a APL GUI. And this is a version of this is a screenshot from a solution we came up with, which I quite like. I think just because it looks like lightning, really. And this is the setup for the final problem. So you were asked to model a imaginary company, and you're selling shoes or whatever you like, and you want to calculate the likelihood of different amounts of profit. And that's given by this formula up here. And the components of the formula are dependent on certain conditions. So there's a defined economic climate. There's 4 of them. There's a likelihood that that climate is going to occur. And then depending on the climate, you got 2 different values which will go into your formula up here. There's another point, which is the cost of a unit is based off a triangular distribution. So it's somewhere between $5 and $8, but it's most likely to be $7. And over here, we notice that the fixed cost is constant. So first of all, I realized that I was going to have to create a way of generating random numbers based off a triangular distribution. So I thought I'd show you that function first. It's up here. And essentially, it's a little bit of arithmetic to convert a uniform distribution between 1 and 0 into a triangular distribution. The left argument is the number of random numbers you want. The right argument defines the triangular distribution where A is the minimum, B is the maximum, and M is the mode. An interesting point, I think originally when I wrote this the first time, this section over here where between 9 and 11 was actually a little nested defin that did a for each on each element, and then did a check, is it over the maximum value or the threshold value, or is it below it? And depending on which one it is, it would do the appropriate right or left arithmetic, which was fine for a couple of hundred, even a couple of thousand random numbers, but as soon as you stuck it up to 1 million, it was just taking a bit too long. So I found it interesting that it was easier for me to actually calculate all of the left-hand values and all the right-hand values. And when I say left and right, the way I think about it is, on the side of the triangle, you got your left side and your right side. So calculate all of them, and then calculate a Boolean that says another Boolean, a length of 1 million, for instance, that says, is it over the threshold, is it not over the threshold, and then simply mask them. So you've created more data, but it turns out it's a whole lot quicker. This is the final code that essentially the answer creates buckets. So it will be, within intervals of $10,000, for instance. So within, 0 to 10,000, what's the likelihood that we'll make this much profit? Between 10,000 and 20,000, what's the likelihood we'll make this much profit? And this is the function that achieves that. Another interesting point that I think I would bring up quickly is the create climate. It's another function that I had to sort of fiddle with in order to get it to work efficiently. I think to begin with, I was asking a whole bunch of if statements. If it's this, give the answer 1. If it's that, give the answer 2. Because I defined the different economic climates by 1, 2, 3, and 4. But I found out if I just did 4 different booleans and added them together, I would be able to get that same result. So we can see over here, we get 1 with 10%, 2 with 30%, 3 with 40%, and 4 with 20%. And then using that, you create whatever your number of iterations are. Send that through there, you got your climate for whatever number of iterations you want to achieve. And using your climate, you can create the 3 values that we looked at before, being the units sold, the unit price, and the unit cost. Then uses the random generation of numbers from the last function.
I have a question. On line 9, isn't my line?
Cool.
Yeah.
Yeah.
On line 9,
Sure.
I just learned this, isn't that a series of numbers from 0 to 1?
It is, but if
Floating point numbers. And so how does one use that to index on line 11?
Because we use the function create climate. So it creates, for instance, in this one, I think it's 10,000 random numbers between 0 and 1. And then it converts those random numbers using the create climate function into numbers between 1 and 4, which have the distribution defined by the table before.
Excuse me.
Sure.
That is exactly the interval index function. I just want to point out.
Oh, brilliant. Well, there we go. Yeah, so I mean, this is it. This line 18 still needs a bit of work. Interestingly enough, before lunch, I tried this same code on version 15, because I wrote this on version 14.1. And this line took an extra 3.3 seconds. Yeah. Yeah, but let's see what we got here. Yeah, so before I...
That's also interval index.
All right. Brilliant. Sure. All right, I think I'm going to say some thanks quick. I'd like to thank, I guess, Ilse Nell first to introduce me into this world and gave me the shot to learn APL. And then I'd like to thank the Dyalog team for putting this together and getting me out here. Yeah, thank you all very much.
Zack, it looks very smooth when you present it like this, and you may not be able anymore to remember the answer to this, but I wonder which part of this had you beating your head against the wall, if any. Where was your biggest breakthrough in working on this?
I suppose the biggest breakthrough would be back to, let me see if I can find it. It was this guy here, the floors and ceilings. That little bit of code over there made my life a whole lot easier. Because before that, I was trying to work out, different cases, and this is the problem-solving competition. And you don't want to have to list 6 different cases, in order to complete this function here. As you can see, this area bit over here, that's actually really 1 line's worth of code. But I thought I'd split it up because it just looks nicer. But then using this bit here and just applying the area twice, it really made the whole lot better.
Thank you for the really nice presentation and talking about your thoughts, which I thought were very APL-ish, and I was impressed that you came to thinking about in a way that seems very familiar to me, even though you're not so familiar with the language. By the way, maybe I didn't hear the beginning. What is your field of study at college or university, whatever you call it?
So I'm studying mathematics and economics.
Oh, well, why do I say oh? Because point about mathematics, which isn't something, I think it's not something I figured out myself, but when I was finishing high school, which was a couple of years at least back, I don't remember exactly, I had a job working for who was then a psychology professor at Stanford, Pat Suppies, who later became one of the pioneers of computing for some reason. Maybe people saw an opportunity. Anyway, he was doing some experiments for which he needed a distribution of random numbers to feed to the subjects, having something to do with flashing lights and guessing and anyway, I don't want to go overboard. But he wanted the random numbers to have a triangular distribution. And what I remember from that experience is that if you add two uniform distributions, you get a triangular distribution.
Right.
And I thought as mathematicians, we should have thought of that ourselves.
Yeah. You bring up a point about this looking APL-ish. I think it was mentioned that I didn't know any programming languages before I discovered APL. And I think that has something to do with it for sure. Oh no, I'd never programmed before in my life. Yeah, exactly. So loops, I mean, I've had to play with some JavaScript, and it shocks me what I have to do to try and create the simplest thing. Are there any other questions?
Thank you.
Cool. Ciao.